Hi everyone. In this session, I'll be looking at what we call the T distribution. It is a special continuous distribution, which is very important in our current applications. But before we can continue, you need to be familiar with the normal distribution, the standard normal distribution, in other words, z-scores, and sampling distributions. Right, so just a quick recap regarding sampling distributions. If we have a population, which we denote by x, and it has a mean mu and a variance sigma squared, then when we select all possible samples of size n, and we calculate the average for each of those samples, and we calculate the expected value of that population of averages, then we get mu. We saw in a previous session that the variance of those averages, the variance of those sample averages, in other words, the variance of the population of averages, is equal to the original population variance divided by n. Because the bigger the samples become, the more values we select from our population, and the closer the sample average becomes to the population mean. So because the population, or rather because the sample average moves closer to the population mean as the sample size increases, it means that the variance of the means decreases. Right, and then when it comes to the shape, we have the Central Limit Theorem, which says that if we have a normal population, then the distribution of the averages, or the sampling distribution of x bar, will also be normal regardless of the sample size. However, if we have a population that's not normal, then the distribution of the sample averages will be approximately normal when we have samples that we consider large, which is at least 30 observations. Right, now let's have a look in a little bit more detail at this. The Central Limit Theorem. Now, in this calculation, we have our sigma square, which is the population variance. Now, it doesn't always happen that we actually know the population variance, because remember, to know a population variance, we needed to study the entire population and measure every single observation, which is not always possible. So in many cases, we don't have the population variance. So what happens when sigma square is unknown? Well, if the population variance sigma square is unknown, then we have to use S square. Now S square is the sample variance. So in other words, we're not going to be using our population variance in our calculation, we're going to use our sample variance. But now there's a problem with this. For every sample that we select, the chances are almost zero that we're going to get the same sample variance. Remember, different samples mean different statistics. So different samples will probably give us different averages, it will give us different variances. However, it's all for the same population, which has a variance of sigma squared. So because the sample variances are different to each other and they're different to the population variance, when we put them in our calculation to calculate our z-score, we don't actually have a z-score anymore, because the z-score is for sigma, which is the population value. But we are now using a sample value. So the sample value is an estimate of the population value. We saw this in a previous session. A sample value is called a statistic, and it's used as an estimate for the population value, which is called a parameter. Now you'll notice that the calculation is the same. The only difference is that instead of using a sigma, we are using an S. But because of this estimate S that's being used, we can't say that this is Z. So it becomes something else. It becomes what we call a T. Now this T, we say, has a T distribution, and it has this parameter which we call nu. Now this parameter over here is called nu. It's a Greek letter, and it is equal to the sample size minus 1, n minus 1, and we say that nu equals the degrees of freedom. Now, the reasons for this terminology is not important right now. What you should know is that when we take out our population standard deviation, because we don't have it, to take it out of the calculation, we replace it with our sample standard deviation, which is an estimate of the population one. We can't use Z anymore, so that's why we have this inequality. But we changed the name to a T, and the T will be dependent on the sample size. Now if we just use a bit of common sense from what we saw earlier on, then what can we say? We can say, well, if the population has a parameter sigma and the sample has a statistic S, and we increase the sample size, make it bigger and bigger and bigger, and every time we calculate S, what is eventually going to happen? Eventually the sample will become so big it's going to be like the population. So that means when we calculate S for a very, very big sample, it's basically going to be equal to the population parameter sigma. So that's why T is dependent on sample size, because as the sample size becomes bigger and bigger and bigger, S becomes more like sigma, so our T over here becomes less like an estimate and it becomes more like Z. Okay, so that's just using a bit of common sense from what we saw a moment ago. Now, let's look at the properties of T. Well, T approximates Z. Now what is Z? It is simply a distance. In other words, a number of standard deviations. And we can see from the calculation here that T is also a number of standard deviations. However, T is a number of sample standard deviations and not like Z population standard deviations. Okay, so it's a number of sample standard deviations, and as the sample sizes become bigger, T should become more like Z. Now, T has the same symmetry properties as Z, for obvious reasons, because T approximates Z, so they should have the same properties. So that means that the probability of being over here, this green, will be the same as this green over here. In other words, being less than negative T value will be the same as being greater than the positive T value. So if this was a negative Z score, then being less than the negative Z score will be the same as being greater than the positive Z score. So they have the same symmetry properties. T is dependent on sample size. As I explained a moment ago, the bigger the sample becomes, the more the sample statistic S becomes like the population parameter. So that means our T will become a better estimate. In other words, it will become more like Z. So obviously T is dependent on sample size. Right, we have T tables, which gives us very much the same information as the Z tables, except it's estimates. Because T is an approximation of Z, the T tables will be approximations to the Z tables. And then lastly, which I've mentioned a few times now, for large samples, T is actually the same as Z. Now, this is an extract of a T table. So you'll see usually at the top of the table, they show us what information we can get from the table. Don't be concerned with this result over here. This is just the PDF of T, which is a bit intimidating, but we're not going to be working with that. What we should know is that the table gives us cumulative probabilities, but it also gives us the complement of the cumulative probabilities. So let's see. To read our T table, we need to know the degrees of freedom. Now here on this table, the degrees of freedom is denoted by an R, whereas previously I said we denoted by this sign nu. This is a Greek letter, nu. It looks almost like a V, but a little bit curved. But it's the same thing as R. And the degrees of freedom will be n minus 1. So in other words, we'll take our sample size, we'll subtract 1 from it, and we'll look for that value over here. Then on the table itself, we have our T values. Now for the Z table, we have the Z values in the first row and in the first column, but not for the T table. The T table contains the T values on the table itself. Then in this first row over here, which is highlighted in blue, we have the cumulative probabilities. So that means if I have, for example, a T value of 2.571 with 5 degrees of freedom, in other words, 5 degrees of freedom means a sample size of 6, then the probability of being less than or equal to this will be 0.975. So in other words, 2.571 will be the cutoff point, 2.571, that's going to be that value over there, and then the area to the left of it, this whole area here, will be 97.5%. Right, and then if we look at the green over here, that is simply the complement of the cumulative probabilities. We call them the tail end probabilities because they are sitting in the tail. They're usually small probabilities and they're on the right hand side. So if we take the 0.6 and the 0.4, we'll get 1. So if we have a T value in this first column, let's say for example 0.265, then the probability of being less than this value will be 0.6 and the probability of being greater than it will be 0.4. Now, our T table contains only positive T values, but because it's like Z scores and it measures the number of standard deviations, we know that T values, like Z values, can be negative or positive. t values and z values, which are both the number of standard deviations, but remember z scores will be population standard deviations, whereas t values are sample standard deviations, they can be below or above the mean. So that means they can be negative or positive. But because of symmetry, it's very easy to actually obtain the values. So that means if I, for example, am interested in this area to the left of this t value, and let's say that this t value is 2.5, okay, that t value is negative 2.5, I'm interested in being less than it, it's going to be the same, or rather, not 2.5, there should be 1.5, negative 1.5, it'll be the same as being greater than positive 1.5. These two probabilities will be the same. So that means I need to know what my degrees of freedom is. In other words, I need to know my sample size, then I subtract 1 from it, and then over here I will just look for t equal to 1.5. Let's suppose that I have a sample of size 5, so that means my degrees of freedom, which is r, will be 5 minus 1, which is 4. Okay, so I'm looking at 4. So over here, the closest I have to 1.5 is 1.533. The probability of being greater than this is 0.1. So that means this is equal to 0.1. So by symmetry, the probability of being less than negative 1.5 is also 0.1. So that is how we use our t-table. Now, on this page, I have the t-table and an extract of the z-table. And you'll see that I have a break over here in the middle of the t-table. I took out a big chunk of it. At the top of the table, we only have degrees of freedom 1, 2, and 3. And then we have the bottom part of the table, where we have degrees of freedom 29, 30, and then infinity. So there's nothing after 30 for this t-table. Now the reason is what I mentioned before. The t is an estimate of z. And the bigger the sample becomes, the more the sample becomes like the population, and the more the estimate, or the sample statistic, becomes like the population parameter. So let's see what that means. If I were to take 0.6 on the t-table, okay, this is a left probability. In other words, if I draw my t-curve, there's the middle of 0, 0.6 probability, so that's going to be that area, 0.6. And I look for the same on the normal table, 0.6, then I see that it's going to be over here. I don't have 0.6 exactly, I have 0.5987 and 0.6026. So my value that I want will be in between these two, my probability, okay, my cumulative probability. So if I look at this, then I see that my z-score for 0.59 is 0.25. So let's write 0.25. And the z-score for 0.6026 is 0.2, 0.2, and a 6. So my one that I wanted is for 0.6, which is in between there. So that means my z-score will be in between. It's not going to be 0.25, it's not going to be 0.26, it's going to be between the two. If we have a look at the t-table, 0.6 cumulative probability, right at the bottom, where we have a very large sample, in other words greater than 30, we have a t-value of 0.253, which is between 0.25 and 0.26. So it seems like this t-value could in fact be the same as the z-score. So let's see. If we look at the next one, cumulative probability of 0.75. So if we look for that 0.75 on our z-table, we have the same problem as before. We don't have 0.75 exactly, we have a value just below and a value just above. So if we look at the value just below, this one over here, 0.7486, then we have a z-score of 0.67. So 0.67 is our z-score, and for the one just above, it's 0.676. So this one can have a 0 there. If we look at the t-table, then we see that our t-value for 0.75 probability, okay, just to remind you, 0.75 probability will be that area over there, that's 0. So this is saying that the t-value is 0.67. So my t-value there, 0.674, and it seems like the z-value could be equal to that, because our z-value lies between these two over here, and this is 0.67 and this is 0.676. So 0.674 definitely lies between them, so it could very well be the one that we are interested in. So let's take the next one. If we look at the cumulative probability, 0.9 on our t value, on our t table, and we look on our z table, we're in luck. We actually have 0.9 sitting over there. And if we look at the corresponding z score, it's 1.282, and we go to our t table, 0.9, we actually have 1.282. Now, if you look at the rest of it, so for example, if you take 0.95 and you look on your extended z table for 0.95 and all the others, you will in fact see that these values at the bottom for a sample size that's very large, these are in fact z scores. So this entire last row is in fact a row of z scores on the t table, because, as I said many times now, as sample sizes increase, the sample statistics eventually become equal to the population parameters, so we don't have estimates anymore, we have the true values. Right, let's have a look at an example. Similar to what we had before, an electrical firm manufactures light bulbs. Let X represent the life and hours of these bulbs. The distribution of X is fairly symmetrical, and it has a mean of 800 and an unknown variance. So now the population variance is unknown. Find the probability that a random sample of size 25 will have an average life less than 785 hours. It is known that the sample variance is 1600 hours. So this is fairly symmetrical, a population mean of 800, but an unknown population variance. We have a sample of size 25, and we're interested in an average life of 785 hours. And then they tell us the sample variance is 1600. So that means graphically, according to our central limit theorem, we can still work with a normal distribution. So that means we'll still have x bar with 800 being in the middle, because that's the population mean. And according to the central limit theorem, it will also be the mean for x bar. So we're going to have this. Remember, 1600 over 25, that is the population variance over n. But what do we have in this case? We don't have the population variance. We have in fact the sample variance. So this will be approximately normal. But that means now we can't use z scores. We're going to have to use a t because of this s squared that we're using. So let's see. Instead of calculating the number of standard deviations and calling it z, we'll calculate the number of standard deviations and we'll call it t. We'll still have x bar, we'll still subtract the mean from it, and we'll still divide by the standard deviation. So this is going to be 785 minus 800 divided by 40 over 5, because remember 40 is the square root of s squared, which is 1600, and 5 is the square root of 25. Okay, so it's the square root of that. This is the one that I'm using over here, 40 over 5, and that gives us negative 1.875. So that means the probability of x bar being less than 785, which is what we want, okay, the probability that the average, okay, find the probability that the average of a sample of size 25, okay, the average is less than 785. So we'll have the probability of x bar being less than 785, and we see that 785 is the number of standard deviations, negative 1.875. Negative because 785 is below 800. So when we take 785 minus 800, we'll get a negative result. There's negative 15 over here. And when we divide by the number of standard deviations, we get the distance. So negative 1.875 is our distance. In other words, the number of standard deviations. But it's not z, it's t. For the simple reason, unknown population variance, so we had to use s squared. And of course the sample size is small, it's less than 30. Remember on the table, as soon as we go greater than 30, then we can use our z. So that means we need to use t, so we'll go to our t table. Now, if we look at the probability calculation over here, it's less than negative 1.875. So we have a negative t over here, but we don't have negative t on our table. So that means by symmetry, we can look at the probability of being greater than positive 1.8. Okay, remember by symmetry. Here we have negative 1.875. We're interested in that area, that probability, but it's going to be the same as that one. And of course here we're going to have positive 1.85. Okay, and we know that we can find the greater than probability on our t-table because it's just the little subscripts over here. Remember the top one, that's the cumulative, the bottom one over here is the complement, and here we want the complement of the cumulative. So let's see. We need our degrees of freedom so that we know which row to look at. Because remember, sample size for the t-distribution is very important. Bigger the sample, the closer the t becomes to our z. So the degrees of freedom will be sample size minus 1. So that's 25 minus 1, it's 24. So that's why we're looking at this row 24 over here. The next thing, I'm going to cut out this middle part because I'm only interested in this bottom row and the headings over here. So if I cut out that part, I can zoom in a bit, we can see better. So row 24. And next I'm interested in this t value 1.875. However, we don't have 1.875 in this row. Remember, the t is continuous. And what do we know about continuous random variables? They have uncountable many possible values. So we can't have a complete t-table. Okay, so these are the most common probability and t values that we'll use. But now in this case, unfortunately, we don't have 1.875. We've got 1.7 and we've got 2.06. And we know 1.875 lies in between those two. So that's not too difficult, because what it means is that our 1.875 will have a probability that lies between these two. For 1.7, we have a tail end probability of 0.05, and for 2.064, we have a tail end probability of 0.025. So 1.875, we want a tail end probability, so our tail end probability will be between those two, 0.05 and 0.02. So that means we can simply write that the probability that we want will lie between 0.025 and 0.05. So graphically, this value over here will be greater than 0.025, but it will also be less than 0.05. And we got that by symmetry from the right hand side by looking at the probability of being greater than positive 1.8 and equating that to being less than negative 1.8.